Okay, kids, we're back here. A little bit different today because I really can't draw diagrams as well as they do in the textbook with my freehand. So we're going to use the textbook. I'll just lead you through this one section today, 14.3. And it's all about electric generators. There's two kinds, alternating current and direct current. And like the word says, electric generator, it generates electricity. So it provides electricity that so many of our devices run. We have huge electric generators here in Niagara Falls at the Sir Adam Beck generating station. And as water falls, that falling water loses its gravitational potential energy and turns into kinetic energy and turns a turbine which is connected to a generator, and through the magic of magnetism, we get electrical current. So that's what it says here in the textbook. The electric generator is a device that converts mechanical energy into electrical energy by rotational motion from continuous sources of energy such as wind, you see them around, falling water, tides, steam, and the construction of a generator is identical to that of an electrical motor. It just works in the opposite direction. Now you're going to read this section on your own, but I'm just going to lead you through this diagram here. And here is a one loop generator, which makes no sense. You would never do that. I've added a little drawing here. This would be a handle here rotating it, or a turbine being pushed by water or steam or wind, something. But these wires have to turn. So this wire here is being forced upward by the rotation, and this end of the wire loop is being pushed down. So that's what we have right here. Look, force on the conductor, that comes from the handle. Now remember what we learned from Faraday and Lenz. This is being forced upward. Well, that means that a magnetic field is going to be created by an induced current in this wire right here that is going to oppose the motion, right? So if you get your right hand out and you stick your thumb into the page, into the screen, and you stick your open-handed fingers running from north to south because of the external magnetic field, you'll see that your palm is facing downward. It's trying to oppose this force. And that opposition is what creates the current in here. So that's the force on that. Then this comes over to the other side. So what it's saying is this turns and comes over to the other side. And here, if you apply the right-hand rule, once again, it's going to try to oppose this force on this conductor. This conductor is being forced downward here. It's going to try to oppose this force. So if you use your right hand here, you stick your open palm fingertips from north to south. So fingertips go from north to south. Your thumb's going to be pointing out of the page. And look, your palm's facing upward because that current pointing upward is creating a force to oppose the motion that created it. So now this wire here used to have this part of the wire right here. This part of the wire right there used to have current going into the page. Now it's got current coming out of the page, and that continues through the loop. So we moved further into the chapter, or into the section, I should say, and we're going to talk about alternating current electric generator, AC generator, and it's connected to what they call slip rings, ring 1 and ring 2, and brushes, brush 1 and brush 2, which are stationary. Let me try to explain this to you. Here are the brushes. There's a brush 2, brush 1, and they literally touch these rings that rotate along with the coil. They're just showing one loop here. In a real generator, there'd be many loops. They're showing, and I hope you saw that in the video. So this is being rotated. So somewhere out here is some external force that's causing the rotation. Okay, and it's connected to these rings that rotate along with it, and these brushes that are stationary. Now, there's two sides to this loop. They didn't put it in the textbook, but I think it'll help with the explanation. Here is the side I'm going to call A, and here's the side I'm going to call B. Now, as we saw a few moments ago, when this is being pushed upward, a current is produced that is shown here. Here's the direction of the current. Then side A moves to the top. There's no magnetic field there. Side B moves to the bottom. There's no magnetic field there. So there's no current being produced. But then side A is being brought down. So side A goes from left to top to right. And as we saw in the previous diagram, now the current in side A is in the opposite direction than it was. Look, see? First it's going into the page, now out of the page. So the current that is being produced in the circuit out here where the galvanometer is, a very sensitive ammeter, look how the current's direction has changed. Here it was clockwise, here it's counterclockwise. And then eventually A gets to the bottom where there is no magnetic field and thus no current. So if we were to take a look at the induced current that's being produced, it's not a constant current at all. It builds to a maximum, decreases to zero, and then actually starts going in the other direction, building to a maximum and then back to zero. That's why it's called alternating current, because it goes one way and then the other. That's how that one works. A direct current electric generator, and it's kind of direct current. It's not the kind of current you'd get from a battery that would just be constant in one direction, not changing. So it's kind of a variation on it. How do we get that? Well, the slip rings of an AC generator are gone, okay, and the slip rings of the AC generator are gone, and they are replaced by a split ring commutator, and that allows it to kind of produce this kind of DC current. I'll show you it on the next page here. So here it is. It's a ring that's split in two. That's what it is. It's like if you have a ring on your finger, picture it being in two halves, and at the top there's a gap, and at the bottom there's a gap. Kind of like this. There's a gap, there's a gap. It's a ring that's been split in two. So same idea here, but it's different here, okay? And what happens here is you've got the brushes still. Brush 1, ring 1, brush 2, ring 2. And you still get the idea of there's two sides to this loop, A side, B side, and A goes from left. Now A is on the top, now A is on the right. Now A is on the bottom, and then it will go back to the top. So think of the loop as having two sides. So similarly as before, this is going to create a current, and I'm showing you that in the black. All right. Then we get to the top, no current because both sides are out of the magnetic field. Then it swings back this way. So once again, the A side of the loop is going to have current in the opposite direction, but now ring 1 is touching brush 2 because of the split ring. See, it used to be ring 1 touching brush 1, ring 2 touching brush 2. Now it's ring 1 touches brush 2, ring 2 touches brush 1, and that split ring arrangement keeps the current over here moving in the same direction. Look what they've got here. Look at the direction of the current here. Look at the direction of the current here. It's the same. And that is done by the split ring. All right. Let's see what that looks like. See, here is the current right there. It increases, gets to a maximum, goes to zero, then increases, gets to zero again, but it never flows in the opposite direction. If I were to graph what a current would, like direct current electricity, what it would look like from a battery, it would look like this. Right? Constant, boom, never changing. So this is a pretty good approximation to a direct current because it's not changing direction, but it does fluctuate a bit. Now there are other devices that try to clean this up to have it approximate this more. But nevertheless, it's always moving in the same direction. It's not alternating its direction. So technically, it's still moving in one direction, therefore direct current. So I'm going to have you read this. I did find some videos for you to watch. You should do that. Read this. I think it's only one question that I gave for this section. Okay, and have a great day. Bye-bye.